Let's recall that in the previous number theory video, we established this congruence when we were trying to show that the converse to Fermat's little theorem is false. Now, over 2500 years ago, Chinese mathematicians made a claim. They conjectured this. An integer n is prime if and only if n divides 2 to the power n minus 2. In the context of number theory, here n of integer of course means a positive integer, and IWF means if and only if. We write that in short like this, you probably already know. It's not a very bad, it is false actually. It's not true. This conjecture is false, but it's not really a bad claim either, because it turns out to really be true provided n is at most 340. But the above congruence shows that the claim fails when n is 341. If you express this as a divisibility relation, you of course get this. And we have already seen that in spite of this, 341 is not prime because 341 is 31 times 11. Despite the failure of this conjecture, composite numbers n which satisfy this condition have remained with us, and they have gained a name. They are called pseudoprimes. So this is the definition. A composite integer n is called a pseudoprime. This is one word, okay, pseudoprime, if n divides 2 to the power n minus 2. Or if you express this as a congruence, 2 to the power n is congruent to 2 modulo n. So clearly 341 being composite and having this condition satisfied for it is an example of a pseudoprime. In fact, this is the smallest one. The next three are these: 561, 645 and 1105. Now what we are going to see today is that there are infinitely many pseudoprimes, and that can be concluded from this next theorem. In the text it is theorem 5.2, and the statement is this: if n is an odd pseudoprime, then the number mn, which is 2 to the power n minus 1, is a larger one. So mn is then a larger number. Of course, it's clear that this is larger than n, but it is also a pseudoprime. So let's see the proof. From the definition of a pseudoprime, it's clear that the proof has two parts. In one part, we have to show that mn is composite, and then in the other part, we show that this divisibility relation is true for mn. Let's start by noting that since small n is a pseudoprime, small n itself is composite. Since n is composite, So n has a non-trivial factorization Rs for some integers R and S satisfying these inequalities. To have a non-trivial factorization, the divisors must be both different from 1 as well as n. That's why we have strict inequalities, and between them of course there is some inequality. They may actually be equal. That will happen if n is a perfect square. So that possibility is also there. Okay. Now let's recall an exercise that we solved way before in the second section of the second chapter, section 2.2, and that is exercise 21. If you see it, you will remember it. Now, y exercise 21 of section 2.2, 2 to the power r minus 1 is, it divides 2 to the power n minus 1, which is mn. So in that exercise we proved that if n has a divisor r, then 2 to the power n minus 1 has this divisor 2 to the power r minus 1. That was the exercise. Okay, so we have found a divisor of mn, but that alone won't let us claim that mn is composite. Who knows, maybe this is mn itself, or maybe this is 1, but that's not the case because of these inequalities. Why? Let us see. First of all, note that since r is strictly less than n, 2 to the power r minus 1 is strictly less than 2 to the power n minus 1. This is a well-known fact, or you can prove this by induction. That means this number is actually less than mn. It cannot be equal to mn. Moreover, since r is greater than 1, this will itself be greater than 1. This becomes 1 in only one case, namely when r is 1. In that case it becomes 2 minus 1, which is 1. For higher values of r than 1, this is also greater than 1. So we now note this. Since 1 is less than r and r is less than n, there is no need to include s here in this part, because we are not concluding anything about s. We have 1 less than this less than mn. So now we can claim that mn is composite because this divisor is a non-trivial divisor. So mn is composite. Next we have to show that divisibility relation. Now since small n is a pseudoprime, small n divides 2 to the power n minus 2 by definition. That we are going to now use. Since n divides this, we have 2 to the power n minus 2 equal to nk for some positive integer k. Now we consider an expression, a number. You will understand why we are considering this afterwards, after we do the calculation. Let us consider this. 2 to the power mn minus 1 minus 1. Let's see what it is actually. What is our mn? Mn is 2 to the power n minus 1 itself, another minus 1. So that means 2 to the power mn minus 2. Oh, sorry, what the hell have I written? 2 to the power n minus 2 minus 1. But this is nk, 2 to the power nk minus 1. Now we can realize this thing, this difference like this also. The kth power of 2 to the power n minus the kth power of 1. And this is where you can use a well-known identity from algebra. Note that k is a positive integer. K can be 1, 2, anything. And that identity is this. Two to the power n minus 1 times the power of 2 to the power n, which is the previous one. This is the kth power, the k minus 1th power, plus the k minus 2th power. Like that, it becomes smaller and smaller, and eventually we have this, and then plus 1, this identity. In fact, you already know, of course, you may know this identity, but special cases of this identity are more well known. For example, from this identity only you have that formula for a cube minus b cube. A cube minus b cube is a minus b times a square plus ab plus b square, that thing. And in fact, the other even more familiar formula is a square minus b square, which is a minus b times a plus b. So those are special cases of this identity. So what do we now get? This is nothing but mn. Mn times an integer. After all, it looks long, but it is still after all an integer, and that is why this number is divisible by mn. You can clearly see that. So mn divides 2 to the power mn minus 1 minus 1. Okay. This implies so if mn divides this, mn will also divide 2 times this number. Or we are almost there. So if we multiply this by 2 using that rule of exponent, this becomes 2 to the power mn, and that becomes 2. So this is what we wanted to show. Besides the fact that Mn is composite. Hence, Mn is a pseudoprime. And that completes the proof. How does this result imply that there are infinitely many pseudoprimes? See, we have already encountered one. This is an odd pseudoprime. So by the above result, this is a larger one. Okay. Then again applying that result, this is another one, still larger. So you can continue like this. So without any end to this sequence, you will keep getting larger and larger pseudoprimes. And that's how there are infinitely many. This of course won't give you all the pseudoprimes. For example, you can imagine how large this number will be. And this one will be even larger. So you will miss those pseudoprimes which we have noted, 561, those things. So that's what we wanted to establish today. Besides this notion, so once you have pseudoprimes, you can go for a class of numbers not just with this 2, but with any base A greater than or equal to 2. So that gives us another class of numbers which are like pseudoprimes. In fact, there exist some numbers which satisfy this pseudoprime definition for any base A, for all bases A. Namely, they satisfy this divisibility criterion. They are called absolute pseudoprimes or Carmichael numbers. In the next video, we are going to study a little about them, and that will in fact conclude this section, and then after that there are exercises. So let me wrap up here itself today. Tomorrow also we have an upload, and because we have already seen topology previous Tuesday, so tomorrow let's go back to differential equations again. We have done that preliminary classification, and then we will see what comes after that. Okay, so see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.